Because so many people get confused between Lenz's law and paramagnetism and diamagnetism, here's a very quick clarification. Let's start with paramagnetic materials. It's easy to remember if you think about the P. Paramagnetic materials pull into magnetic fields. Again, paramagnetic materials such as aluminium pull into magnetic fields, but it's an incredibly weak effect. It's very hard to detect. So no, paramagnetism cannot lift maglev trains, and copper is not paramagnetic. Copper is diamagnetic. So that's paramagnetism, not to be confused with Lenz's law. If either the magnet or the piece of aluminium in this case is moving, that invokes Lenz's law and invalidates your attempts to detect paramagnetism. Both the magnet and the aluminium would have to be stationary. Once it begins moving, it's inducing current in the aluminium, and therefore invoking Lenz's law. Diamagnetic materials such as copper do the exact opposite. So D for deflect. Diamagnetic materials deflect out of magnetic fields, unchanging magnetic fields. But again, it's a very, very weak effect. It's very difficult to detect. Again, if there's any movement between the magnet and the material, that invokes Lenz's law. Lenz's law tries to stop either of those things happening. Right, so this is Lenz's law. Top diagram. When you're pulling the conductor out of a magnetic field, it attracts. It doesn't want to be pulled out. It resists. It opposes the motion. That's Lenz's law. Look at the bottom diagram. When you try to push it into the magnetic field, it repels. It tries to stop you put it into the magnetic field. It resists. It opposes. That's Lenz's law too. Both are Lenz's law effects. This is commonly called the induction braking effect or magnetic braking, Lenz's law braking effect. This is why it's hard to generate electricity, because the more electricity you use, the harder it is to generate that electricity, the harder it is to physically turn the generator, because the current that's being generated, that's being used to heat your hairdryer or cook your chicken in the oven, whatever, that current has its own magnetism, which always opposes the motion which induced it in the first place. In other words, when the conductive material is moving towards the field, it's pushed away. When it's moved out of the field, it's pulled back again. Lenz's law describes how nature tries to stop you generating electricity effectively. It tries to maintain the equilibrium. It doesn't want you to generate electricity. That's why you have to put in physical effort. That's why electricity is expensive. So, Lenz's law. Copper, aluminium, etc. only become strongly magnetic in a changing magnetic field. In other words, when you're either moving the magnet or moving the conducting material, you're inducing current in that material, and that current will always be in such a direction as to cause a magnetic field that opposes the motion that's causing the induction in the first place. That means whether you're pushing it into the magnetic field, that will be resisted, or you're pulling it out of the magnetic field, that will also be resisted. Look at the top and bottom example. The polarity changes whether you're moving it into the field or withdrawing it from the field. That's Lenz's law. Most people think that induction braking is simply all about repulsion, because they look at maglev trains and see how they appear to float on the rails, repelled from the rails, and think, so that's Lenz's law. It's repulsion. No, that's only half the story. The other half is the top diagram, explaining how if you try to lift that train off the rails, it would be pulled back towards the rails. Maglev trains are a little bit counterintuitive because we can only appreciate that they're being lifted from the rails. We cannot immediately appreciate that they're also being stuck to the rails. We don't appreciate that if we turned the rails upside down, the train would be suspended from the rails. It would be stuck to the rails just as much as it's lifted off the rails. That's Lenz's law. It does both. It pushes against pushes and pulls against poles. The induced current changes direction when leaving the field from when entering. So the magnetism of the current always changes to make it hard to move the conductor at all. In simple terms, whichever way you try to move the conductive material in a magnetic field, towards or away from it, the current induced by that movement has its own magnetic field, which always opposes that movement, makes it hard to move it.